So before going to start this particular session, I want this prerequisites of this particular session is you need to familiar with Mealy FSM design and more FSM design so that the things will be little bit easier to understand what are we discussing. Okay. Now, so before going to actually start about how we are going to develop your Verilog code for your More or Mealy FSM design, first of all, let us try to understand how to design your Verilog code for a simple Mealy FSM. Okay. Now, let's say if I have a simple Mealy FSM sequence detector, if I have a simple Mealy FSM sequence detector like this. Now, what do you mean by sequence detector and what do you mean by Mealy FSM sequence detector? This and all things you can watch it in our digital design playlist where we have discussed it in a very elaborated way. Okay, so all the possible cases, those and all things we have discussed in our digital design. So you can watch it in our playlist. Now, let's say if I want to develop a Verilog code for a Mealy FSM sequence detector. Okay, now how it is going to look like, the block diagram of that particular Mealy FSM sequence detector is going to look like this. Input, we are going to apply a serial data. This is a serial input, and we are going to have a reset signal and a clock signal we are going to provide, and this is my output. Okay, so let's say if I want to detect a sequence 1 1 0, and from LSB onwards I'm going to provide my input to my design. Okay, now whenever if I apply 1 1 0 to my input, then my output should become 1, else my output should become 0. Okay, now for that we already know the state diagram of how it is going to look like. One more time I'm going to draw that for 1 1 0 how it is going to look like. If I apply my reset signal, then I'm going to a state which is known as ideal state, and if I apply one more 1, then I'm going to stay in the same state and your output is equal to 0. But if you're going to apply 0, you're going to next state which is known as S1, and your output is still equal to 0. And if you are going to apply one more 1, if you are in S1 state, then you are going to a state which is known as S2, and your output is equal to 0. And if you are in S1 state and if you are applying 0, you are going to stay in the same state. Okay, and from the S2 state we are going to consider a non-overlapping Mealy FSM we are going to consider. So that's why how I'm going to draw is, if I'm going to apply 1, then I'm going to a state which is known as ideal state, and my output is equal to 1. And if I'm in S2 state, I have the sequence 0 1, and followed by if I get one more 0, then I can reutilize this particular 0. So that's why I'm going to a state which is known as S1 state, and my output is equal to 0. So this is how I'm going to develop a state diagram. Now, even if you are doing this in digital design, or if even if you are doing this in Verilog design, you need to draw the state diagram. State diagram is compulsory. Okay. Now, from the state diagram, if I want to draw a circuit diagram, then how to draw that? So I'm not going to do all the steps. I'm just going to mention those. You can draw it on your own. So first of all, I need to draw the transition table, or you can say excitation table, using this particular state diagram. Okay. Next, what I should do is, after drawing this excitation table, I need to find out my outputs for each and everything. Using this transition or excitation table, I need to find out my inputs. So let's say if I'm going to consider a D flip-flop, then I need to consider, first of all, how many flip-flops do I need for this? So I need 0. How many states are there? 1, 2, 3. So total I need 2 flip-flops. Okay, so I just need 2 flip-flops for achieving these 3 states. Okay, so I should find out D1 and I should also find out D2 using key map. By from considering your transition table, you can get your D1 and D2. Okay, now so after that, this is how we are going to get our simplified diagram. I'm going to directly draw the particular simplified diagram, how it is going to look like. I will show you, because we need this particular simplified diagram to understand how we are going to develop our code. So this is my first D flip flop, and this is my second D flip flop, and this is my D naught, Q naught, D1, and Q1. This is Q1 bar and Q naught bar. Okay, and this is my clock. And for D naught, I'm going to provide my input from this NOT gate, and for D1 I'm going to provide the output of this AND gate, and directly from here I'm going to provide the input to this, and here I'm going to get one more thing, and here I'm going to get my output, and this output is being fed from here and from here. Okay, and we are going to give here. Yes. So this is how your circuit is going to look like. How I'm drawing the circuit? I'm basically drawing the transition table, and I'm determining the values of my D0 and D1, and from that, using the K-map or by solving that particular things, I will get the equations for my D0 and D1, and after getting the equations for my D0 and D1, I'm going to draw this particular thing. FSM design steps you can follow for designing this particular thing. Okay. So this is how, first of all, we need to draw this FSM, and there is no necessary that you need to draw the FSM for each and every time. Just for explaining some concepts, I'm drawing this FSM for the very first time. And from next onwards, when we are developing our Verilog code, we are only going to draw the state diagram. There is no need to draw the circuit diagram. Okay. Yes. Now, let's say if uh, if I have a single flip-flop like this, D naught, D and Q bar. Okay. And here I'm going to provide my input. And this is my clock. And this is my reset signal. Now, let's say if I apply my reset signal, then what is your output you are going to get? If I'm going to apply my simple reset signal, then what is the output which we are going to get? We are going to get 0. That we already know. And if we apply 1, then what is the present state of this particular flip-flop? The present state of this particular flip-flop is equal to 1. If you are going to apply 0, then what is the present state of your input? It is equal to 0, right? So this flip-flop output is nothing but your present state. This flip-flop output is nothing but your present state. Present state is nothing but what is the output of this particular flip-flop. And this is a sequential logic, and this is a sequential logic. Okay, so if you are going to apply 0, then at your output you are simply going to get 0, and if you are going to apply 1, then you are going to get simply 1, and if you are going to apply 0, then you are going to get your output as simply 0. That is nothing but your present state. Present state is nothing but this is output of your flip flop. Like this, let's say if I have one more circuit diagram, and if I have a AND gate followed by a NOT gate, and one more OR gate, some random circuit I'm going to have like this. Okay, and let's say I'm okay. Let me not make it as complicated. Let me keep it as simple. Simply, we will keep one NOT gate which is connected to our input. Okay, and this is my clock. Now, let's say initially, if we apply my reset signal, then what is going to happen? Initially, if I'm going to apply my reset signal, then my output will be equal to 0. Okay, this is my present state. This is my present state. What is my present state? Present, what is the output of your flip-flop? That is your present state. Now, how you are going to decide your next state? Let's say if you are going to apply 1 at your input. Okay, so before your positive edge of the clock, you are going to apply 1 here. Okay, so if you are going to apply 1, then what is your next state? How your next state is going to be decided? So if you are going to give 1, then you are going to get 0, and your output of this particular flip-flop is equal to 0. So this next state is basically decided by your combinational logic. So what should be your next state? That is actually decided by this combinational logic. Whatever the input you are passing to this particular combinational logic, that is deciding your present state. Okay, so that's why here next state is basically decided by this combinational logic, whereas your present state is basically decided by this sequential logic. Okay, now coming to our FSM state diagram, FSM circuit diagram, which we have drawn for a sequence detector 110. Let's say our initial present states of this flip-flop. What do you mean by present state? Present state is nothing but my output of this flip-flop. So here let me change the color for this. Let's say here my output is equal to 0 and my output is equal to 0 initially if I apply my reset state. Okay, so my present state, that is nothing but q0 is equal to 0 and q1 is equal to 0. Okay, now Let's say if I'm going to apply the input as 0. Let's say if I'm going to apply the input as 0, then what is going to happen? This input is going to be traveled through this combinational logic, and it is going to be fed to this D flip-flop. And from here it is going to be given to this AND gate, and it is going to be fed to this second D flip-flop. And again it is going to feed to your output. Like this you are going to give. Now, let's say if I am going to apply 0 next, what is your, if you apply 0, then what is your next state? Next state is basically decided by this combinational logic. Okay, so you are going to get 0 at your input here, and here, since one of the input of your AND gate is equal to 0, your output is equal to 0, and here also you are going to get 0. Okay, now, so what is your present state at the next edge of the clock? At the second edge of the clock, you are going to get Q naught is equal to 0 and Q naught is equal to 1 because it is a NOT gate, right? Q naught is equal to 1 and Q1 is still equal to 0 because we have 0, right? Yeah. So at the second edge of the clock, this value will be updated, but this value haven't been updated in the second edge of the clock. Now, let's say if I am going to apply 1 at the input, then what is going to happen? This 1 will be traveled over here and it will become 0. And this 1 will be traveled over here, and one of the input of your AND gate is 1 and another input is also equal to 1. This is the input which we have got from the previous stage. So at the third edge of the clock, what is going to happen is the second flip-flop input is equal to 1 and the first flip-flop input is equal to 0. So at the third edge of the clock, Q0 will be equal to 0 and Q1 will be equal to 1, and the output of this gate is nothing but it is still 0 only because initially we are having 0, right? So that's why output is still 0 only. Let me write it down. Now, let's say if I'm going to apply one more one. So before fourth edge of the clock, I'm going to apply one more one. Then this will be traveled over this NOT gate. And my output of this NOT gate is still 0. And so we are going to get your Q naught is still 0 only. Okay. And so one of the input of your AND gate is 0. Your output will be 0. But we have already 1 which is applied to previously before in the third clock edge. So before the fourth, so exactly at the fourth edge of the clock, your output of this second flip-flop will be made to 1, and here we have already 1 that will be traveled over here. So here your output will become 1. At the fourth edge of the clock, Q0 will be equal to 0 and Q1 will be equal to 0 only, but your output will become, sorry, Q1 will be equal to 1 and your output will become 1. So this is how you are going to get, after getting the sequence 0, sorry, 1 1 0, your output is going to get 1. Okay, now if I want to wrap up this particular whole diagram into a particular architecture or block diagram, then this is how it is going to look like. So we are going to have a sequential logic. You can see here, right, there are two D flip-flops. This D flip-flops are basically used to determine your present states. Okay, so we are going to use the sequential logic for determining our present state. Now, for determining our next state, we have this combinational logic, right? So that's why we have one more block, which is a combinational logic block, where we are going to apply our input. Our input is not directly applied to the sequential logic. You can see our input is applied via this combinational logic, and this combinational logic is basically determining the state. Okay, so that's why my input is applied to this combinational logic, and the output of this combinational logic is given to your sequential logic. I'm drawing this block diagram from this diagram, okay, from this circuit diagram. Now, how I am getting my output? The output of this present state is given to again a combination logic, and from this combination logic we are getting our output. Okay, so how to draw that? So from this present state, from this sequential logic, we are getting my output, and this is again fed to the combination logic, and from here we are going to get our output. I'm referring to this diagram. So from this sequential logic, it is passing to the combinational logic, and from this combinational logic, we are getting our output. And you can see here, this output, we have a feedback connection to the input. So where is it? Yeah, from here we are having a basically a feedback connection to our input. Okay, so from this state, from this present state to input of this combinational logic, we will have one feedback. And if you carefully observe in this diagram, input has a direct connection over to the output. Okay, so that we are going to draw it. So input will be connected like this to the output combinational block. Okay, so this particular block we are going to implement it in Verilog. This we are going to implement it in Verilog. Okay, so using this particular block diagram for Mealy state machine, we are going to implement it. So is it clear how I'm drawing this and how I'm going to analyze the things? Is it clear? And you might have seen this particular block diagram a number of times in many so many places. Like we for FSM we are going to draw combination logic, sequential logic, combination logic. But the exact reason why this particular block diagram is referred is it is taken basically from the circuit diagram. So as we have discussed how your block diagram of your FSM is going to look like. So using this particular block diagram, we are going to, okay, great. So using this particular block diagram, we are going to develop our Verilog code. Now, if I want to write down a FSM, a finite state machine Verilog code development, then how to write it? Now, I'm going to declare my module. This is common thing, and declare my input ports, output ports. This is common. Okay. Next, what I should do is I'm going to declare two variables. Okay. One is reg present state, comma next state. This variable is used to decide your present state, and this variable is used to decide your next state. Okay. Now, before that, we need to declare some states. Like in this particular example, we have how many states? Three states. One, two, three. Now, for this, I am going to use something known as parameter. Now, what do you mean by parameter? Let me show you what do you mean by parameter. So basically parameters are nothing but they are named constants. For example, let's say if I have a literal one tick binary 0, or let's say if I have two tick binary 0 1. Okay, and if I want to write down or let's say if I have a simple number 7. Okay, now if I want to write down reg 7 down to 0, a is equal to 5. Okay, now instead of writing this number as it is, hard coded number, what can we do is we can use a parameter. So instead of writing the number, or instead of writing a number constant, we can give a name to that particular number. Okay, so parameters are nothing but there are named constants. So instead of writing that particular number, we can use this named constants. Why, sir? Why should we use? I will explain you. There is a concept which is known as parameter overriding that we will discuss. Okay. Now, what we are going to do, we are simply going to write down reg. So let's say instead of writing this number 7, what I'm going to do is I'm going to declare a parameter. Parameter width is equal to 8. Okay. Now here what I'm going to write down, width minus 1 down to 0, a is equal to 5. Okay, so instead of writing this number 7, what I can do is I can use this parameter width. Okay, please remember this is not a variable, it's an alias. Okay, or it's an alternate name for this particular constant number. Okay, and why we are going to use for reusability purpose, that I am going to explain in later sessions. But please remember this width is not a variable, parameter is not a variable, it's a named constant. Okay, now we have simply written width minus 1 down to 0. That means width is nothing but 8 minus 1, that is 7 down to 0. So instead of writing this 7, I can write down width minus 1 down to 0. Now, same in this particular thing also, I'm going to declare few parameters. So parameter ideal is equal to 2 tick binary 0 0. So instead of 0 0 writing everywhere in my code, I'm going to write down parameter that is nothing but ideal, and parameter S1 is equal to 2 tick binary 0 1, and parameter S2 is equal to 2 tick binary 1 0. So instead of writing this constant number values everywhere inside my code, I'm going to use this particular parameters. Okay. Now, So how many states we have? Three states. So for storing this particular three states, we need 2 bit, 1 down to 0, present state comma next state. Okay, PS comma ns. So this is how we are going to declare all our variables which are necessary. Now what are we going to do? We are going to write down our present state logic. We should write our present state logic. Now, what do you mean by present state logic? You can refer this particular diagram which I have drawn here. The logic which is going to decide your present state, that is nothing but your present state logic. This we need to write down, right? Yeah. So how to write down? So present state logic is a sequential logic. Okay. So present state logic is a sequential logic. Why present state logic is a sequential logic? The reason I have declared previously only. It is a sequential logic. You can see from here also. So your present state is determined by your flip-flops, which are your sequential blocks. Okay, so that's why your present state logic is a sequential logic. Okay, so always at the rate passage of clock, or if your design is working on the negate of clock, you can write down always at the rate passage of clock. What you're going to do is, whenever if you are going to apply your reset signal, then your present state should be in your ideal state. Else what you should do? Else, you can see from the block diagram that this combinational logic is determining your next state, and that is being assigned to your present state. Okay, so that is what I am going to write down. Else, my present state is equal to next state, and followed by begin and end. That's it. This is my present state logic. Simple. Okay. By referring to the block diagram, I have written my present state logic. Okay. I hope you are following me and it is clear. Please let me know if it is not clear or if you are facing any difficulty in any particular logic. Now, next what I am going to do is I am going to develop my next state logic. Now, how to design your next state logic? So basically next state logic, it's a combinational logic. Why it is a combinational logic? This just now we have seen, right? So your combinational logic, your next state logic is a combinational logic. Now, how to write your next state logic? Always at the rate star begin. Now I'm going to use my case statements. Case of my present state. Now, if my present state is equal to ideal, if I am in ideal state, then what should I do? Then I'm going to check for my input. Okay. If my input, let's say my input I am declaring it as dn. If my dn is equal to 1 tick binary 0, I should go to next some state, else I should go to some other state. The condition, according to the state diagram, you can write down this particular condition. Next followed by end. And if you are going to S1 state, then if your input is equal to 1 tick binary 1, then you should go to some state. What is the state, sir? By referring to that state diagram, we can decide. Okay. Else, if my input is equal to 0, I should go to some other state. Okay, what is that state? It will be decided by our state diagram. We will decide it from our state diagram. Okay, so like this, for each and every stage, for each and every state, we are going to write down each and every possibility of your input. For each and every state, we are going to write down our each and every possibility. If you are in a particular state, then if you are going to apply one input, then which state you should go. Okay, and that state updation will be happened in your sequential logic. Okay, you can see that PS is equal to NS. So the NS value will be updated to the PS at the positive edge of the clock. But NS value will be updated whenever you are going to change your input. As soon as you change your input, the NS value will be updated immediately. But from the NS to PS, this value will be updated only at the positive edge of the clock. Please be careful about this. Okay. So this is how you are going to write down your next state logic. So how to write our output logic? Now, if we are developing our Mealy state machine, then our output is dependent upon our state as well as your input. Whenever there is any change in your input or whenever there is any change in your state, then your output is going to be affected. So you can include your output inside this case statement only, or else you can write down one more always block and you can write down that particular output logic. Okay, that and all we are going to discuss later. Okay, so how to write down your output logic for your Mealy state machine and how to write down the logic for your Moore state machine, and what are the different coding styles which you are going to follow for your Mealy state machine and for Moore state machine. That we are going to start our discussion in our tomorrow session, and we are going to wrap up this FSM with that. Okay, yes. So that's all about this particular session. If you have any doubts or any queries, you can stay and discuss with me, or else you can leave the session. Okay, thank you.